obstruction to weak approximation from a prime with quick reduction. Thank you very much.
Okay, so good morning, everyone. So first of all, thank you very much for the invitation. I'm really happy to give this talk. And so today I will talk about an example I worked on during the first month of my PhD at Leiden University. And this is an example of a K-tree surface in which there is a prime with good reduction that play a role in the Brauer-Manin obstruction to weak approximation. So in the first part of my talk, I will introduce some tools that are needed to define the Brauer-Manin obstruction to weak approximation. And then in the second part, I will focus the attention on my example and try to give some ideas behind the construction of this example. Okay, so let's start with some notation. So during this talk, I will denote by K any number field, and by this capital omega K, the set of places of K. So for every place nu in this capital omega K, I will denote by this K nu the completion of K at the place nu. So if you're not familiar with this, just think about the rational number. In that case, the set of places consists just of the primes together with the so-called place at infinity. And for every prime, these K nu are the p-adic numbers, while for the place at infinity, we get the real number. And for my example, it is enough to think about rational number and p-adic number. Okay, so moreover, we will denote by X a smooth, proper, and geometrically integral K variety. And so what we are interested in studying is the set of K points on X. So the first thing we observe is that for every place, we have a natural inclusion of the K points inside the K nu points of X. And therefore, we can look at the K points of X inside the product over all the places of the K nu points of X. And since these fields K nu are topological fields, the idea is that we can put a topology on the set of K nu points of X. So roughly speaking, this K variety X is locally the zero set of some polynomial equation. And therefore, at least locally, we can think about the K nu points of X as a solution of polynomial equation. And so we can naturally see this set of points inside K nu to the end and put therefore a subset topology on it. And the idea is that one can generalize this to the whole set of K nu points of X, even in the case where X is not a zero set of polynomial equation, but just locally a zero set of polynomial equation. Okay, so the question we are interested in is the following. So what does the image of the K points inside the product over all the places of the K nu points of X look like? So we're ready to define what weak approximation is. So since I told you in the previous slide that we can put a topology on this set of K nu points, we can also put a topology on the product, just the product topology. And we say that a variety X satisfies weak approximation if the image of the K points inside this product over all the places of the K nu points is dense. So let me give you some example and non-example of variety that satisfy weak approximation. So the first one, and probably the easiest one, is the projective n-dimensional space. And one can prove that the projective n-dimensional space satisfy weak approximation. And maybe a more interesting one is the one given by smooth projective quadric. And one can prove that smooth projective quadric always satisfy weak approximation. And let me just mention a non-example. So if we look at the projective variety defined over the rational number by the following equation. Okay, so Selmer has proven that this equation admits a Q nu point for every place nu. This just means that this equation has a p-adic solution, a non-trivial p-adic solution for every prime p, and has a real solution. And Selmer has also proved that this equation does not admit a rational solution, a non-trivial rational solution. So this means that the set of rational points is empty, while the product over all the places of the Q nu points in this case is non-empty. So of course the set of rational points cannot be dense inside this product. Okay, so Manin in the 1917 has introduced the so-called Brauer-Manin set, which is a set contained in the product over all the places of the K-nu points of X. And the idea of Manin was to use the Brauer group in order to build a set which is intermediate between the closure of the K points on X and the set of all the places of the product over all the places of the K-nu points of X. So his idea was to build this subset of the product and show that this subset is a closed subset and contains the K points. And from this follows that we have this chain of inclusion. So the idea is that in general, to study K points on a variety can be extremely hard, and also to describe the closure of the K points inside the product over all the places can be extremely hard. And while this Brauer-Manin set is in general easier to describe than the closure of the K points. And so in particular, now we can define what the Brauer-Manin obstruction to weak approximation is. We say that there is a Brauer-Manin obstruction to weak approximation on X if this Brauer-Manin set is a proper subset inside the product over all the places of the K-nu points of X. So this is called obstruction to weak approximation because if this Brauer-Manin set is a closed subset of this product, then the set of K points of X cannot be dense inside the product over all the places of the K-nu points of X, just because of this chain of inclusion. Okay, so I will not go into the details of the construction of this Brauer-Manin set, but I just want to mention one of the main ingredients needed to construct this Brauer-Manin set, and yes, and tell you something about this this ingredient. So as I anticipate, this Brauer-Manin set involves the Brauer group. And in particular, for every element in the Brauer group and for every place nu, we have an induced map called the evaluation map that goes from the K-nu points of X in the Brauer group of K-nu. And we say that a place nu play a role in the Brauer-Manin obstruction to weak approximation if we can find an element in the Brauer group of X such that the evaluation map associated to it from the K-nu points of X in the Brauer group of K-nu is non-constant. So in particular, like if one go through the definition of this Brauer-Manin set, it appears that if the evaluation map at some place is non-constant, then there is a Brauer-Manin obstruction to weak approximation. So really, to study these evaluation maps is the right thing to do in order to understand how this Brauer-Manin set look like. Okay.
Excuse me. What's the Brauer group of K-nu?
So for local fields, it can be proven that the Brauer group of a local field is isomorphic to the quotient of Q over Z, while for the real number, this K-nu can be either local fields or the real number or the complex number. So for local fields, you have that these Brauer groups are just Q isomorphic to Q over Z, while for the real number, it is just a group of order 2 generated by the Quaternion algebra, the Hamilton Quaternion algebra, and for the complex number is trivial.
Right, okay, thank you.
Okay, So people have started to find way to describe this Brauer-Manin set. And in particular, there is this question asked by Swinton-Dyer, which it's really relevant for my example, because in my example, like I anticipate you that in my example, we show with a concrete example that the answer to this question is negative. So Swinton-Dyer asked the following question. So if we start with a variety such that the Picard group of the variety of the base change of the variety to the algebraic closure of K is torsion-free and finitely generated, and we denote by S the finite set of places containing the Archimedean places and the place of bad reduction for X. So I will come back to this in a moment. But then he asked, is it true that the only place that can play a role in the Brauer-Manin obstruction to weak approximation are contained in S? So like the question is it true that if we put this additional condition on the Picard group, then for every place with good reduction, the evaluation map is constant? And so what are these place of bad reduction and place of good reduction? So if we start with again, just an idea, if you think about a variety defined by some polynomial equation, then this polynomial equation have coefficient in the field K. And after clearing the denominator, you can assume that this polynomial equation have coefficient in the ring of integer of K, so that you can look at the reduction of this polynomial equation modulo primes in the ring of integer of K. And a variety has good reduction at a prime if when you look at the reduction of this polynomial equation modulo this prime, this still define a smooth variety of the same dimension. But like, yes, this is just an idea of what good reduction means. It's not really the proper definition of it, but I think like it's enough to understand what I will say in my example. Okay, so in 2020, Bright and Newton proved a theorem that already say that in general, the answer to the question asked by Swinton-Dyer is negative. And in order to state this theorem, I also have to tell you what good ordinary varieties over a perfect field of characteristic PR. So like usually people are more familiar with good ordinary, what ordinary means for elliptic curves and abelian varieties. But Bloch and Kato have defined this more in general. So this is, if you look at elliptic curves and abelian varieties, you find back the usual definition of being ordinary. And so if we start with a variety Y, which is smooth and proper over a perfect fit of characteristic P, then we denote by this BYQ the X at Q4 on Y. And we say that Y is ordinary if the cohomology group of this sheaf BYQ vanish for every N and Q. Okay, so now we can state the theorem proved by Bright and Newton. So they have proven that if we start with a smooth proper variety over a number field, such that there is at least one non-trivial global 2 form on X. And if we pick a prime, this Gothic P, so it's a prime at which X has good ordinary reduction. And I will denote by this normal P, the residue characteristic of Gothic P. Then there exists a finite extension of our field K and a prime P prime lying over P, and an element in the Brauer group of the base change of the variety to L, which is, like with this, I mean that this element has order a power of P, such that the evaluation map associated to this element from the LP prime point on X to the Brauer group of LP prime is non-constant. So in particular, if we are able to show that there is a variety such that the picker group is finitely generated and torsion-free, and it has at least one global to form, then we are in the setting of both Bright and Newton theorem and Swinton-Dyer question. And we can use this theorem to give a negative answer to the question. So like the point is that varieties with torsion-free picker group that is finitely generated and with at least one non-trivial two global form exist. And an example is given by K3 surface. So let me just recall what K3 surfaces are. So a K3 surface over a number field is a smooth geometrical integral two-dimensional K variety such that the first cohomology group of OX is 0 and the canonical bundle is trivial. So let me just state these two facts. So the first one is that it can be proven that the picker group of a K3 surface over the algebraic closure is always torsion-free and finitely generated. And the second fact is that there is always at least one non-trivial two form on X. So moreover, Bright and Newton have proven the following thing. So if we start with a place with good reduction such that the ramification index is strictly less than p minus 1, where again this p is the residue characteristic of this Gothic p, then the evaluation map from the Kp points of X to the Brauer group of Kp is constant. Okay, so I'm mentioning this fact because the idea of my example is to try to build the easiest possible example of a K3 surface where this phenomenon occurs. And so to look at a K3 surface that is defined over the rational number. But if we start with a K3 surface defined over the rational number, then for every prime p different from 2, the following relation holds true just because the ramification index is 1, and which is strictly less than p minus 1 for p different from 2. And therefore, the evaluation map is constant, which means that for every prime different from 2, this prime cannot play a role in the Brauer-Manin obstruction to weak approximation because the evaluation map attached to it is constant. So if we want to find a K3 surface defined over the rational number such that a prime with good reduction play a role in the Brauer-Manin obstruction to weak approximation, we need a K3 surface that has good reduction at the prime 2. Okay, so this was the first observation, crucial observation in the construction of the example. So now finally, I will introduce the example. So X is the K3 surface defined by the following homogeneous polynomial of degree 4 in the three-dimensional projective space. So it can be proven that in general, smooth homogeneous polynomial of degree 4 always define a K3 surface. So this is a K3 surface. And one can show that this has good reduction at the prime 2. And let me just stress that here, it just really means that if you look at this polynomial equation, modulo 2, then it defines a smooth variety over the projective space over F2. And we have the following result. So the class of the following Quaternion algebra, so it's the Quaternion algebra defined by the following function, C as element in the function field of X, defines actually an element in the Brauer group of X. And one can prove that the evaluation map from the Q2 points on X to the Brauer group of Q2 is non-constant. And finally, one can prove something even stronger, which is that the rational points are not dense inside the Q2 points of X. So I will go really quickly through the main step in the proof of this theorem, because I think that like the proof is quite straightforward, while I think that the interesting part of this example is how we came up with this quaternion algebra. So what were the idea behind the construction of this quaternion algebra? So I will spend a little bit more time in giving you some idea behind this construction. And yes, but so let's start with the main ingredient in the proof of the theorem. So in order to show that the quaternion algebra A defines an element in the Brauer group of X, one can use a purity theorem for the Brauer group. So purity theorem is give you like a recipe to detect if an element in the Brauer group of the function field of X defines an element in the Brauer group of X. And one can really just apply this theorem and see that actually this element defines an element in the Brauer group of X. So moreover, in order to see that the evaluation map from the Q2 points on X to the Brauer group of Q2 is non-constant, one can just find two elements in the Q2 points of X. So these are just two non-trivial two-adic solution of the equation, such that the evaluation map computed at X1 is different from the evaluation map computed at X2. And in order to show that this the set of rational points is not dense inside the set of two-adic points, the idea is to prove that for every place different from 2, the evaluation map is constant and trivial, and use this to conclude that this obstruction is concentrated in the Q2 points on X, and therefore the rational points are not dense inside the Q2 points. But yes, this is really just an idea of how the proofs goes. And before giving you some idea behind the construction of A, I want just to mention that another property of this quaternion algebra A, which is the following. So we denote by this Brauer-1 of X, the algebraic Brauer group of X. This consists of those elements in the Brauer group of X that becomes trivial in the Brauer group of the base change of X to the algebraic closure of K. And there is this result proven by Koliotelin and Skorobogatov that say that for algebraic element in the Brauer group of X, and for every finite field extension of the p-adic number where P is a prime with good reduction for X, the evaluation map from the K points to the Brauer group of K has to be constant. So this means that our quaternion algebra is not an algebraic element in the Brauer group of X, because I mentioned that our variety has good reduction at 2, and the evaluation map from the Q2 points on X to the Brauer group of Q2 is non-constant. And so this is a transcendental element in the Brauer group of X, and like usually to construct a transcendental element on K3 surface is something difficult, but like somehow here it was surprisingly easy to construct this element. So yes, this is an observation I wanted to make. So let me mention something about the construction of this quaternion algebra. So the first thing is that that I want to tell you is this relation between the quaternion algebra A and two forms and a two form. So let me be more precise. So if we denote by Y the K3 surface over F2 defined by the same equation, essentially the same equation defining X, just look at the equation modulo 2. Then since it has, again, since X has good reduction at 2, this when we look at this equation modulo 2, it still is a smooth polynomial, and therefore it defines a K3 surface in the three-dimensional projective space over F2. So by the property of K3 surface, we have that the global two forms on Y is a one-dimensional F2 vector space. And so it really consists just of one non-zero element, omega. And one can actually write down, at least locally, how omega look like. And if one go through the definition, it can be like proven that omega is of the following form. So it's of the form df over f, wedge dg over g, where this is f and this is g. And we see that this function is strictly related to the function defining our quaternion algebra A. Indeed, like if we call f tilde the same function, now we see at the function in characteristic 0. So I'm sorry, there is a little bit an abuse of notation because I'm denoting with the same letter the variable over f2 and the variable in x, so over the rational number. But the idea is that if we denote with this f tilde and g tilde, these two lifts of f and g over q, then really these are lift of the function f and g. And so this quaternion algebra A, it seems to be strictly related to the one non-zero element in this h0 of y omega 2y. So now the question is like, why there is this relation between what happened in characteristic 2 and what happened in characteristic 0. And the bridge between what happened in characteristic 2 and what happened in characteristic 0 is given by a result proven by Bloch and Cato. So I need to introduce a couple of objects. So the first one is this f, which will be the function field of y. So this is a field of characteristic 2. And we will denote by this omega q f log the logarithmic q forms on f. And this is just the subgroup generated by elements of the form dy1 over y1 wedge dyq over yq. And so another things I need to introduce is this field k, so capital K. So if we denote by x2 the base change of x to the 2-adix number, then this capital K is the function field of x2. So this is a field of characteristic 0 that contains the rational number. And Bloch and Cato have defined a decreasing filtration on the cohomology groups of Galois cohomology groups of K with respect to this Galois module mu p tensor Q. And they have proven that there exists the following isomorphism, which is the isomorphism that give us, again, like it gives us the bridge from characteristic 2 to characteristic 0. So there is an isomorphism between the logarithmic Q form, direct sum, the logarithmic Q minus 1 form on F, and the quotient of this Q cohomology group with the first piece of the filtration. And so now I want to tell you why this is related to the Brauer group. So if we assume that our field K contains a primitive P root of unity, then we have an isomorphism between this Galois module mu P tensor 2 and mu P. And this gives us an isomorphism between the second cohomology group of mu P tensor 2 and the P torsion of the Brauer group of K. And therefore, we have an induced isomorphism that, with abuse of notation, I will still denote by rho 0, that goes from the 2 logarithmic forms on F, direct sum, the 1 logarithmic form on X, on the quotient of the P torsion on the Brauer group of K, with the first piece of the induced filtration on the Brauer group, on the P torsion of the Brauer group of K. So in particular, like one can give an explicit description of this map, and this map send a global A2 form to the class of the Quaternion algebra given by y1 tilde and y2 tilde, where these yi are just any lift, these yy tilde, sorry, are just any lift of the yi to the field K. Okay, so again,
I'm sorry to interrupt you, Margherita. We're just a little bit short on time. Okay.
Okay.
Yeah,
yes.
So you feel free to finish, but just keep this in mind. Thank you.
Okay, thanks. So why is this related to the Quaternion algebra A? It is because, like I already told you, that we can write omega in the following form. So omega can be seen as a logarithmic 2 form on the function field of f. And we see that this isomorphism rho 0 sends the couple omega 0 to the class of our quaternion algebra A, because these are just two lifts of this function on K. And so these things are related to each other in the following way. But again, like the next question is why we care about this? Like why, if we can build a quaternion algebra that comes from a logarithmic form, then we can hope that this quaternion algebra gives somehow an obstruction to weak approximation. So I will finish by telling you why these two things are related. And the reason is the following, it comes from the following theorem proved by Bright and Newton. So Bright and Newton have defined a filtration on the Brauer group of x2. So x2 again is just the base change of x to the two adix numbers. And this filtration, the n piece of this filtration consists of those elements in the Brauer group of x2, such that for every finite field extension of Q2, the evaluation map is locally constant on the L points on x2, where local is given by this description that depends on n. I will not go into the details of this. But the idea is that the evaluation, that Bright and Newton have proven that the evaluation, the zero piece of the evaluation filtration on the two torsion is given by those elements in the Brauer group of x2 that lies in the second piece of Bloch and Kato filtration. So in particular, our element A, when we look at our element A inside this quotient, since it comes from this element, which is not trivial in the direct sum of the two logarithmic forms with the one logarithmic forms, this element, the class of the quaternion algebra in this quotient is non-zero, which means that our quaternion algebra does not lie in the first piece of the filtration. But again, since the filtration is decreasing, it does not lie even in the second piece of the filtration, which means that our quaternion algebra is not an element in the evaluation zero part of the Brauer group of x2. So at least after, if we take a base change, if we look at least after taking an extension of Q2, we have that the evaluation map is not constant. Okay, so this is just a conclusion slide, which just stress about the two main ideas in the example I talk. And the first is to use, I want to stress that the first thing was to use Bloch and Kato isomorphisms together with the results by Bright and Newton to deduce that if an element A such that the evaluation map on the Q2 points is not constant exists, then A should somehow be related to the only non-zero element in the two forms on Y. And the second main step was to find the correct lift of A, in the sense that to find an element A in the Brauer group of K, such that the image in the quotient comes from the couple omega 0, but also it defines an element in the Brauer group of X. So these were really the two main steps in my example. And yes, with this, I finish what I wanted to tell you. And thank you very much for the attention. And if you have any question, I will try to answer.
Thank you very much. Let us all unmute ourselves and thank Margherita for her talk.